Okay, so this next video, this is going to be Learning Target 20 Part 2. So this is the 12.6 polar graphing part of our lesson this week. So with polar graphing, there are a few different things we're going to do. First kind of way of graphing is we're going to plot points. That's always our fallback, right? Anytime we want to graph and we don't know what the graph looks like, we plot points. And then we're going to use features of the graph like symmetry. We're going to use zeros and something called the maximum value of R to sketch the graph. And then we can also use some special polar graph shapes. So in this video, we're going to focus on 1 and 2. And then 3, this is going to be on the Desmos activity that you have. So let's focus on plotting points and symmetry. So we'll start off with, let's do symmetry, and then we'll do all the features. So we'll do the second bit, and then we'll put that all together with plotting points to graph things. So starting off with symmetry. So just like with graphs, there are 3 different types of symmetries we can have. We can have symmetry with, so let's do this in terms of Cartesian. So we have y-axis symmetry, we have x-axis symmetry, and we have origin symmetry. So when you have y-axis symmetry, if you have xy, that's going to be the same as, if you think about it, xy, if it's symmetric over the y-axis, that means the y-coordinate stays the same, but the x has to be negative. Right, so negative xy. If I think about this, if I have a point on this side, to be symmetric over the y-axis, I'd just have a negative x value, but the y value stays the same. For x-axis symmetry, if I have a point xy, then the x value stays the same, the y value goes negative. Thinking about this on a graph, I have a point, it's x and y. I make it symmetric over the x-axis. Well, then it's going to flip down to negative y, but the x value stays the same. The last one is origin symmetry. If I have a point, xy, well, if I go across the origin, well, that's going to go negative x and negative y. Those are my 3 symmetries in Cartesian coordinates. Right, so Cartesian. So if I now think about my symmetries in polar coordinates, I also have 3 different types of symmetry. In this case, I have symmetry with the line theta equals pi over 2. I can have symmetry to the polar axis, and I can have symmetry to the pole. So the line theta equals pi over 2, that's a vertical line going right through the middle. That's like the y-axis. The polar axis, that's basically like the x-axis. That's when theta equals 0, that line. And then the pole is the origin. It's the same as origin symmetry. So for symmetry with respect to the line theta equals pi over 2, if we have a point r theta, it's the same as the point r pi minus theta, or negative r negative theta. Right? If you think about this, let me move this a bit out of the way. Right, so I have my polar graph and I have a point, and I want it to be symmetric around this point. This is r comma theta, and now I'm going this way. Well, I can either think of it as the same distance r, but if this was theta, this is pi minus theta. That's one way to get it. Or if I go negative theta, right, and then negative r to go in the opposite direction, I'll also get to that same point. So those are my 2 symmetries around this line. For the polar axis, so I have a point, and I want it to go down here. Well, that's the same r, but negative theta. So r theta can be same r, but negative theta. Or it could be pi minus theta, and then in the negative direction. So negative r and then pi minus theta also works. I think about, because these are angles, there are a lot of different ways you can describe them. So there are a few different tests we can do. For the pole, this is on the origin. So if I have r theta, and now my point goes there, well, that's either a negative r, but the same theta, right? I'm going the same distance, but in the same angle, but in the opposite direction, same amount of r. Or it could be going the same distance r, but then pi plus theta. So r theta goes to either negative r theta or r pi plus theta. So again, hopefully you're trying to visualize these things on a graph to get the symmetry, because again, there's a lot of stuff that you could be memorizing, and that's not going to be feasible to just memorize all that stuff, right? Like, I don't have this stuff memorized. I always draw these sketches out to figure out which way, how to test for symmetry, because that's not something I have the brain space for. And so hopefully that's what you're also thinking about in doing these symmetry tests, is looking at just visualizing the graph and thinking about where it's symmetric. So let's practice just with symmetry. So if we have, let's say, r equals 4 plus 3 cosine theta, and we want to test for symmetry in each of these types of symmetry. So we'll do line theta equals pi over 2. So we're going to replace r theta with r and negative theta. And we want to think about, well, will this graph be the same? So, well, I know cosine is even, which means cosine of negative theta is the same as cosine of theta. Well, so that doesn't make the same graph. Let's try with the polar axis. So that's taking r theta, but then replacing r and negative theta. This one is actually going to work out. Going to be the same thing. Now, unlike Cartesian, we can have symmetry with a few different things. So we do have to test all of it. Negative r, and then theta, this one doesn't work. So we can't get it to be r equals the same thing. Here we get r equals the same thing. So we know that this equation is symmetric around the polar axis. Now, important note. These tests are sufficient but not necessary. What does that mean? That means that if you satisfy one of these tests, for example, this one, it satisfies this test, we know it is symmetric around the polar axis. As long as it satisfies it, that is sufficient proof for us to say that it is symmetric around the polar axis. It is not necessary. What that means is, if something is symmetric, it doesn't necessarily pass this test. So, for example, it didn't pass this test with the pole. That doesn't mean we can say categorically it is not symmetric around the pole. We should actually graph it and see. So symmetry tests on polar coordinates are not, these tests are not totally conclusive. If they pass, you know for sure they are symmetric. If they fail, that means try something else. It's kind of like when we did limits, right? Like if we get undefined, that means try something else. It's not done. Like it's not necessarily undefined. This is a frequent thing that happens with math theorems a lot, that when we come up with math theorems, right, we're looking for patterns and we're trying to come up with rules for it. So we have this rule for how symmetry works. Our rules are not strong enough that they work both ways, right? It's kind of like the Pythagorean theorem, for example. That is a really strong theorem because it works both ways. If you have a right triangle, you have this a squared plus b squared equals c squared. And then if a squared plus b squared equals c squared, then you have a right triangle. You know that works both ways. This is not something that does that. This is something where if the test works, you know it is symmetric. But if it is symmetric, that doesn't mean the test will work. So that's what it means to be sufficient, as in if it passes, you know that's enough proof to say it works, but not necessary. It doesn't necessarily have to pass to work. So just remember that with these tests. Right, so you do the test. If it passes, or it can fail. If it passes, you know it's symmetric. If it fails, there's not enough information. That doesn't mean it is not symmetric. So that's what you want to be careful of. You have an example in your note sheet as well for something where if you test for symmetry, it's going to give you something different from the actual symmetry. You also have a few trends that you can look at. So in your textbook and in your note sheet, you have a few other tips that you can look through to guess at symmetry. That will make it slightly easier as well. The other thing is maximum R values and zeros. So maximum R value, so that's just the highest R will go. So you use this, use the amplitude and shift on the sine or cosine piece of your graph to determine this. Right, so for example, you have like R equals 10 minus 10 sine theta. Well, if sine theta is -1, that's an extreme value of sine, right? It can either be 1 or -1. Well, if sine theta is 1, then R is going to be 10 minus 10 times 1, which is 0. But if sine theta is -1, then R will be 10 minus 10 times -1, which is 20. So its maximum R value is 20 because it could go up to 20. It can't go above 20 because the maximum sine can go to is 1 or -1. It can't go beyond that. So we can't get above this, but this is that maximum value that it can hit. Zeros are just solving for this, right? So that I'm not going to go over. We've done a lot of solving trig equations, but that's what you do when you're finding zeros. So I want to go over just how we're going to graph these. So we'll do one graph, and then there's another graph on your note sheet for you to practice on as well. So the main thing we want to look at when graphing is we want to make tables. We're not going to avoid using tables on this. It's something that's really useful for polar graphing. It also helps you, again, like parametric equations, to see directions in motion. And also sometimes when you graph this, because we're using angles and these angles double up on each other, right? They go back on themselves. Usually we think about going from 0 to 2 pi. But you don't always have to go from 0 to 2 pi to sketch something. Sometimes you might finish a graph from 0 to pi. And this is going to be really important in calculus next year because you're going to have some problems where you'll need to know exactly how much theta you need to graph it and not use any excess theta from what you already have. So for example, if you can graph something from 0 to pi, that's all you want. You don't want to double up on it because that's going to mess up some of the calculus stuff you do. So that's not something we're doing this year, but that's more in preparation for next year. So let's look at sketching this. Let's actually, let's change this graph. So I know this is on your sheet. Let's change it to, actually I'll change it on the sheet before I give it to you as well. Let's do this graph instead, 2 cosine 3 theta. So if I look at its, let's make a table. So for tables, we're going to do theta and r, and we're going to pick different thetas. Usually we want to go up in small increments to kind of see how it's going. So let's, we'll we'll make the table and graph it so you can kind of see the direction of this too. So when theta is 0, so we get cosine of 0, which is 1. So r is 2. So at theta equals 0, we're at 2. I'm going to start there. Then let's go up to pi over 6. When theta is pi over 6, actually, since I'm multiplying it by 3, let's do pi over 12. Go up just a little bit. So then 3 times pi over 12, that's pi over 4. Cosine of pi over 4 is root 2 over 2. Times 2 is root 2. So at pi over 12, which is like somewhere around here, we're at root 2, which is about like 1.4. So we're somewhere over there. And so we've graphed this bit now. Then we'll go to pi over 6. And when I substitute that in, I get r equals 0. So that brings me over here. And this is why graphing and table is gonna help, because you can't really see where the angles are when you do this, because your directions are all over the place because of how we're drawing this. Right, because the r value is changing and the angle is changing. So see, like we've just gone back on this. We could have gotten to this point at any angle. So you want to just keep making tables and graphing as you make the table. Let's do pi over 4. That gives me negative root 2. So for pi over 4, and then I go negative directions, so somewhere over here. So I'm going to make this. And then let's do pi over 6. Oh, sorry, we did pi over 3. That's negative 2. So at pi over 6, we're at negative 2, which is down here. And then at, let's go pi over 2, we're back at 0. And you keep filling this up more. So let's do a few more. Let's do 3 pi over 4. So we're kind of getting a sense of the shape. We're kind of going around here. We go around here. I should go down further for 2. So if we continue this, at 3 pi over 4, we'll get to, what are we going to get to? 9 pi over 4, right? Yeah. So 9 pi over 4 is root 2 over 2 again. So that's root 2, negative root 2. Wait, no, positive root 2. So then that's up here. So kind of seeing that we're making this shape. Right? And if I keep going, you'll see I'm going to finish up this petal and then get this petal. My scaling was off, but I make this like rose petal shape. But it went in a certain direction. Right? So if I draw this again, just kind of do it with the shape of this. And I draw it. I started off here. I went here. And then went down. Came back up, went down, looped around, made that. So if you go through your whole table, you'll get that direction on it as well. That's what you want to look at and keep plotting points and graphing it. This is going to be probably a tough part just in terms of precision to really focus and draw these points in and connect them. And again, practice is going to help you on that. So that's what graphing this is going to look like. It's just making a table, plotting those points out, and connecting it all up. Now, one thing that will help is the special polar graphs. That's what you're going to look at on the Desmos activity, and then look at page 790 along with that in your textbook. And that's going to show you some special shapes that we get with polar graphs and what those equations look like. So you're going to look at the table on page 790. You're going to do the Desmos activity that's going to take you through why those shapes happen with those different equations. So then combine those special shapes plus these tables to make these graphs, and then do practice problems from your textbook to really work through it.